even functions are going to be symmetric over the y-axis. And so then it gives us this piece of information here that tells us that f of negative x just equals f of x. Okay, so let's talk about what that means. What it means is if I plug in x or negative x, I should get the same number out, right? So for example, if I think of f of 2 on this graph, and it's really doing crazy stuff there. F of 2, if I look at this graph, f of 2 is right here. It is negative 3. And for some reason, it's like creeping down the page right here. I don't know why. F of 2 is negative 3. On an even function, if I plug in the negative of that number, if I do f of negative 2, here goes, I don't know why. I don't know why it's doing that. It's crazy. All right. F of negative 2 should have the same value. It should also be negative 3. Right here. Okay. So I could look at that for lots of different points, like f of 1. I don't even know what it is. It's like negative 1 point something. Here go my points, like crawling down the page for some reason. But if I look over here, if I plug in negative 1, I also get that same value, right? What happens with this is that because your positive x's and your negative x's give you the same y value, the graph is symmetric over the y-axis. You can flip it there. With odd functions, we're going to have something different happen with this. With an odd function, our graph is symmetric about the origin. And when I used to teach geometry, we had to do origin symmetry. And I used to try to explain this so much. And it was difficult to explain. And I still find it difficult to explain. But what I have resorted to here, origin symmetry is the same as a 180 degree rotation. I'm going to need to not use this Word document. I guess that's the problem. So, like, for example, I can do this up here. You guys can't do. You can do this on your paper. You just need to spin it upside down. Right. If I take this graph and I rotate it 180 degrees, I flip it upside down. Not really a flip, actually. I rotated it till it's upside down. Now, my numbers are obvious. My x and y axes are off because I rotated it. But does the graph look any different than what you see on your paper right side up? So with origin symmetry, if we rotate the graph 180 degrees, either direction, doesn't matter because you'll end up with the same value there. You're going to get the same graph for that. So what you're going to find for this is that if we plug in negative x, we get the opposite of g of x. So let's look at what this looks like for this particular graph. And I wish he had used a graph that had a little better numbers crossing on grid lines, but it doesn't. So we're just going to estimate right here. So for example, I've got f of 1, gosh, this is annoying, is going to equal, like, it's going to crawl down the page again. It's like negative, okay, let me do this. Let me open the PDF version and write on it, because I don't know why it is doing this, but it is annoying. Alright, I'm alright. I know the PDF won't do it. I can't flip things upside down on the PDF, but okay, let's try this. Jesus. Okay, so right here, work? Okay, there we go. So like if I do f of 1, I'm getting like, let's say negative 1.6. Maybe it looks a little further than 1/2 right there. So I'm estimating here. So what should happen if I find f of negative 1 on an even function, I'd still get negative 1.6. On an odd function, I will get negative 1.6 or positive 1.6. The sign will be opposite right here. So negative 1.6 is right here. You can see that is on the graph. There. So you'll have the same absolute value, but it's going to be the opposite sign on an odd problem. Okay. Now, I don't think, let's see if he tells you this. I don't think he does. Let's do these 2 problems and I'll tell you this secret here that he does not reveal on these notes. All right, so sometimes you may be asked to determine if a polynomial is even, odd, or neither just from the equation, and it will not be calculator active, so you can't graph it. If this happens, there's several different ways that you can do this. I used to teach kids to try to do it with the x's. I like the way that Mr. Passwater does this whenever on his solutions for this. He doesn't bother with the x stuff. He just plugs in a number, and what would be the easiest number to plug in? Probably. Well, actually, there's one number that would be even easier, but we cannot use this particular number. We cannot use 0, right? Because we can't have a positive and a negative of 0, so don't plug in 0. What's the next easiest number to plug in? 1. All right, so let's plug in. Oh. Sure that wasn't. Let's plug in 1. So h of 1 is going to be 2 times 1 to the 4th power minus 1 squared. My computer is having a fit today. Why is it not letting me write? Everything's disappeared. Let's try over again. Alright, we're going to have to flip back over to the Word document and try that. Which is our... Oh my gracious. Let's get rid of this. Okay. Let's go back over to the Word document and see if I can get that to work. Alright. So h of 1 is 2 times 1 to the 4th power minus 1 squared plus 5. Now, when I raise 1 to a power, I'm just going to get 1. So this is just 2 minus 1 plus 5, which is going to be 1 plus 5, which will give us 6. So, what I want to do now is I want to plug in the negative of that number. I want to plug in negative 1. Now, this test will fail if you get 0 for that. If you get a 0, then you need to pick another number. You need to try 2 or 3 or 4, or something that won't give you 0. But most of the time 1 works. Occasionally it does not. All right, so if I plug in negative 1, I've got 2 times negative 1 to the 4th power minus negative 1 squared plus 5. Now, when I raise negative 1 to the 4th power, what am I going to get? It's positive 1, right? When I raise negative 1 to the 2nd power, what am I going to get? Positive 1. So I've got 2 times positive 1 minus positive 1 plus 5, which ends up being 2 minus 1 plus 5, which is still 6, right? So I plugged in the positive and the negative for a number, and I got the same y value. If you think about graphing this, what that means is I had the 0.16 right here, and then I've got the -1.6 over here. Pretend those are graphs better. So that's going to be symmetric about the y-axis. This is an even function. Okay, you could do this with any number. It doesn't have to be 1 and -1. You could do 2 and -2. You could do 7 and -7. If 1 will work, if 1 doesn't give you 0, 1's going to be your easier number to deal with. So like if we look at B, if I do k of 1, I will get 1 to the 3rd power plus 3 times 1 minus 1, which will give me 1 plus 3 minus 1, which gives me 3. If I think about graphing it, that's the 0.13. Right here. And then I'm going to do k of -1. So that would be -1 to the 3rd plus 3 times -1 minus 1. Okay. What is -1 to the 3rd power? Is -1. If we raise -1 to an odd exponent, it's going to keep that negative, right? And then we'll have minus 3 minus 1. And that is going to give us -4, -5. So I got the 0.1, -5. I'm sorry, -1, -5. So I've got this. Now, this particular case, I don't get the same number, and I don't get the opposite number either, right? So this would be neither. Here. Okay. Now, let me give you a trick for this that's even easier than this. If all exponents are even, the function is even. Okay, now it has to be an expanded form for this to be true. So like if you have x plus 1 times x minus 4 times x plus 3 where it's in parentheses, you would need to multiply that together before you could do this. But right here, notice I had an x to the 4th, an x squared, and I don't have an x with that 5, but if I did put an x with that 5, what would its exponent be? 0, and 0 is an even number, right? So this x to the 4th, x to the 2nd, and x to the 0 all have even exponents. This is an even function. For the odd functions, it is also true if all exponents are odd, the function is odd. Now, you might look at B here and think, wait, that doesn't seem right. Because I've got x to the 3rd right here, and I've got, this x doesn't have an exponent, so it would have an exponent of 1. 3 and 1 are both odd numbers. Why is that one neither? Beside the 1, we've got x to the power of 0 right there. So that one has both even and odd exponents, so it is neither odd nor even for that. Okay, questions?
So if the exponent has 2 evens and then odd, it's even.
It'd be neither. Yes. Yeah. Yeah. They have to be all even or all odd for it to be even or odd. If you have any that are not, that don't match the others, then it's neither for that. You really don't even have to work them out. Yeah. And the reason that happens is because when you square a negative or raise the negative to the 4th power or to the 6th power, it's just going to give you exactly what you had whenever you put the positive number in, because that gets rid of the sign there for that. But do watch out for that x to the 0 power, because sometimes things look odd but they're not really because they got that coefficient on the end that has that x to the 0 with it. Okay, C and D we're just going to do from looks of the graph. What would you guys say for C? It is odd. If you rotate that 180 degrees, then it is going to be the same. Another thing you can do is just look for points. Like, so for example, here I've got 1, -3 is my point. That means -1, +3 should be on my graph, and it is, right? Or if I do, this one doesn't have a lot of really easy ones to do. I can do this one too. 2, 0 is here. Actually, that looks kind of even because it's still true. 0, the opposite of 0 is still 0, so that's okay. Like, let's just do this point right here. This is like 2.23. That means -2.2, -3 should also be on the graph. So you should see the opposite signs happening there. A lot of times you can just picture it and see it. Sometimes maybe not. What about D? It's neither. It is not symmetric about the y-axis. We couldn't fold this in half. And if we do rotate it, it's going to be an upside-down parabola. It's not going to look the same. All right. So, for end behavior. The end behavior of a function describes how a function hold on. Did I do this or did I would say behaves right there. That might not be what he was wanting. Let me see. I think I did this one. I think I did. Might not have. Maybe that's the worksheet. Let's just pull up his real quick to see what word he's. Yeah, it is behaves. I had it right. All right. Okay. In other words, the end behavior is what happens to the value of y as x increases or decreases without bound. Okay. So there are two ways they're going to have us write this for these problems. You do end behavior in Math 3, and I think that you would say like as x approaches -infinity, f of x, or y approaches blank. Does that seem somewhat familiar, like you've heard that wording before? In this class, we are going to, if it's written out in words, it's going to, I think they're going to word it a little bit differently just based on what I've seen AP put out there. There's a chance they may still word it this way we've seen before. But what I have been seeing on the questions for this is it'll say as the x values decrease without bound. If you are decreasing without bound, you're going down forever, which is -infinity, right? So that would be as x approaches -infinity. And then it'll say the y values of f of x, or it might just say f of x. And then you're going to say that it increases, decreases, approaches a number, whatever happens for that there. So it's similar to this wording. So when you see decrease without bound, you should be thinking -infinity. For that, when you see increase without bound, you should be thinking +infinity. Okay. Now, that notation above it, I do not believe you have seen before. Have you guys seen that LIM with the X underneath it? This is limit notation. Limits is our first unit in calculus every year. So I think they want you to use limit notation here. to just sort of introduce the notation to you for this. So what the way you would read this out here is limit as x approaches negative infinity of f of x is how you would read that. It just means as your x values go towards negative infinity, that's the x approaches negative infinity, what happens to f of x, the y values of that function there. And notice this is your left side of the graph because that's where x approaches negative infinity. If you have x approaches positive infinity, that is the right side of the graph. Okay. So this is new notation, but I think as you see us do the problem, you won't have a lot of issues with that. So let's start from graphs. If we want to describe this left behavior verbally here, this is the only time you do not go from left to right. When we're doing any domain, we go from left to right. But if we are doing end behavior, we want to talk about what happens as we go from the middle to the left side. All right. So verbally, we would say as x values, and I'm going to use the wording that I've seen on a lot of the problems, decrease without bound. Or you can think of as your x approaches negative infinity, as you go to the left side here, f of x. Now, f of x refers to our y values. What are happening to our y values as we go to the left side of this graph? They're going up. And are they stopping anywhere? No. So f of x increases without bound. Now, at least for this one, let me write what we would have written in Math 3 for that. We would have said as x approaches negative infinity, f of x approaches positive infinity. You can if you want. They might use that language on a question because it is correct. It's just two different ways of saying the same thing. That first way of writing it is what I have seen in the AP materials, though, that they have given you. Now, for limit behavior for the left side, this is what you're going to write. You're going to put limit as x approaches negative infinity. So LIM is your limit, x with an arrow, negative infinity, of f of x. You must put f of x right there, or g of x, or h of x, or whatever they've called the function. And then you'll put equals, and then we're going to put the value. So whenever we see that limit as x approaches negative infinity of f of x, that tells us x approaches negative infinity tells me we're looking at the left side. Okay? And again, what is happening to my values on that left side? Y values, what's happening to them? Up and up and up. And where are they going? Positive infinity. So we would put positive infinity right here. If you want, yeah, if you want to put that, it's not necessary on the positives, but if you like to put it there just to make sure you're very clear about it, it's perfectly fine to put it there. Okay? All right, now, right behavior verbally. If we're looking at the right side of this graph, that means if we start somewhere in the middle as we go to the right side, as x gets bigger and bigger and bigger, what's happening to my y values there? They are going down. So we would say this time x is getting bigger, right? So as x values increase without bound. f of x, and since we're going down, we would say f of x decreases without bound. And we could also say, I guess I'll do it on this one too, just this one. We would say as x approaches positive infinity, f of x approaches negative infinity. Okay, for these problems, this first part right here, as x values decrease without bound, or as x approaches negative infinity, that's what tells you you're looking at the left side, right? For this part, as x values increase without bound, or as x approaches positive infinity, that's what tells you you're looking at the right side of the graph. And for our notation here, we would have, with limit notation, we'll say limit as x approaches positive infinity of f of x would equal negative infinity. Okay, questions on that? All right, so to do another problem, left behavior verbally, we would say as x values decrease without bound, we want to talk about what f of x does. So as x decreases without bound, that tells me we're looking at the left side over here. And what is happening to my y values on that left side? Up. They're increasing. So f of x is going to increase.
Even though it decreases the first time.
Right, you're looking at the furthest left. Yes. Because there's no like specific middle point that you are going to start at. Yeah. Right, you're looking at what's happening on at the end, because this is our end behavior. Because way, way, way out here is where x is negative infinity. Right, so we're looking at the very end. So it might do crazy stuff in the middle, but we're talking about what's happening on those ends. Without bound. For limit notation, that would be limit as x approaches negative infinity of f of x equals, and since it's increasing, that's a positive infinity. I think pretty much for everything you're going to see in this unit, your answer is positive infinity or negative infinity. If it's going up on that side, it's positive infinity. If it's going down on that side, it's negative infinity. It is possible for them to like even out at a number to like have a horizontal asymptote. I just don't think you don't see that happen on polynomial functions, so we're not going to see it yet. Right behavior verbally, as x values increase without bound, f of x, what's going to happen on the right side of this one? We look at our right side, way out here on the end, we're also increasing. So it's going to be increases without bound. Okay. Limit notation will look like this. The limit as x approaches positive infinity of f of x is going to equal positive infinity for that. Okay, so example 2 is just asking us to sketch a graph with these properties. When I see x approaches negative infinity, is that my left or my right side? Left. And since it equals negative infinity, is it going to go up or down? Down. Right? And then when I see x approaches positive infinity, that means I'm looking at the right side. And I got negative infinity there also. So that side is going to go down. Right? So if I want to sketch a graph for this, I know this side needs to go down. I know this side needs to go down. You can make this graph do whatever you want it to do in the middle. It does not matter. You could make just a simple parabola. You can do something crazy like I've done here. It doesn't matter what happens in the middle, but those both sides, left side and right side, need to go down. Let's see. Ethan, on B, on my left side, should I go up or down?
Down.
And then on the right side, what am I going to see? Up. So I know this side's got to go down, and this side's got to go up. And then, again, you can do whatever you want in between. Maybe it just looks like this, like a cubic. Maybe it's a straight line. It could be, it would be okay for this one if you wanted to just do a straight line that did this. That would be correct for this. We just know what's happening on the ends by this information. Okay, so a couple of things that you need to keep in mind. For polynomial equations, it is easiest to find the end behavior of the right side first. Okay? On the right side, if your leading coefficient, let's see, it goes up if the leading coefficient is positive, and down if the leading coefficient is negative. Okay? The left side is going to go in the same direction as the right if the degree is even. And it's going to go in the opposite direction as the right if the degree is odd. Notice this is the degree being even and odd, so you're looking at the highest exponent. It's not talking about even and odd functions here. It's just the degree. So, for example, I've got x to the 5th power here. Actually, really, let's not even worry about that first. Let's do right side first. Why is it not erasing? Because it is against me today. So, if I've got a positive leading coefficient, that means my right side is going to go up. Right? If I have an odd degree, that means that the right and the left go opposite directions, so this side would have to go down. So for B, positive coefficient, 1/2 is a positive number, right? Right side goes up. Even degree, left side also goes up. What do you guys think for C? Both down. This -2 right here, that one's not expanded, but that -2 would be multiplied by everything once you did expand it, so that's going to be your leading coefficient. So that flips it upside down where you got both sides going down for that. Okay? Let's see. Maddie, what about D? Is my right side going to go up or down? Okay? For the right side, okay? What's the coefficient in front of that x? There's not one. It is a 1, but it's got that minus that makes it negative. So that right side is actually going to be down. And then your highest exponent is a 5, which is odd. So the left is going to be the opposite. It's going to go up. E is going to be the same because -5x to the 5th is your leading term, right? even though it's not in that order. So you would have the same up here, down here. Oh, and F, can you tell right away on this one? You really got to multiply this one out, and I probably don't have time to do that. So I can't tell right away on that one because it's not multiplied out. You would need to multiply it out, and I think we're out of time on that. So your assignment that I'm going to give you is not actually, we're going to do some more practice of that before we take the quiz on Monday. The assignment that I'm going to give you is from AD Classroom. Now, you don't have to log into AD Classroom. I don't like to do these on AD Classroom when your response because they're hard to type in. So I just printed it. So the questions from AD Classroom. So this is an example of what free response questions are going to look like for you guys. So I need you guys to try these for me this weekend. It's 2 questions. They both have 3 parts. So do your best. The first one is calculator active, so you'll need your calculator to do that. The second one is not calculator active. Okay? And I will post my answers for these as well, so you can kind of check and see what you're doing on those. So we'll talk about these on Monday. We'll practice with end behavior just a little bit more. We didn't quite get to the end of the notes, but we've got the idea pretty much. And then